So you may be very familiar with the set of strings defined over a given alphabet. And so we're going to let sigma star denote the set of strings over the alphabet sigma, and we are going to define this set of strings recursively. So our basis step identifies the initial elements within the set of strings, and so we're simply going to add the empty string as a member of our set of strings. And recall that the empty string is simply a string which has no members of the alphabet in it. Okay, then we need to define recursively how to form new strings from the members already in the set of strings. So our recursive step tells us that if W is a string formed from the alphabet sigma and X is a member of the alphabet, then we simply add X to the right side of the string to form a new string. So what does this look like? So let's look at a usual example of bit strings. So our alphabet is simply the set of numbers 0 and 1 are bits, and the strings are formed recursively according to this definition above. So that means that we begin by adding the empty string, and then as soon as we have a string, a recursive step tells us that we can simply add any member of the alphabet to the right side of that string. So we can take our initial string lambda and add either 0 to the right or 1 to the right, as these are both elements of our alphabet. Since the empty string has no elements, adding 0 to the right of nothing simply gives us the string consisting of 0, and adding 1 to the right of a string which has nothing in it means simply having 1 as a string. And then as soon as these become strings, according to the first application of the recursive step, we can add both elements of the alphabet to the right. So we can add 0 to 0 to get 0, 0 as a string, and we can add 1 to 0 to get 0, 1 as a string. Similarly to 1, we can add 0 to get 1, 0, or we can add 1 to 1 to get 1, 1. And then to each of these new strings, we can add either 0 or 1 to the end. And as you can see, in this way we develop all possible bit strings. We can also use a recursive definition to show that a particular element is a string. So if we look instead at an alphabet consisting of the first two letters of the English language alphabet, A and B, we can show that AAB is in fact a string over this alphabet. So in order to show that this is a member of our alphabet, we have to go through the steps of our recursive definition to show that we can write this following the recursive step. So knowing that the basis step adds the empty string, and then knowing that to any string we may simply add any member of our alphabet, since A is a member of our alphabet, we know that A is then going to be a string, since we would add A to the right of the empty string, which then just gives us A. So A is a string according to the recursive definition applied to the empty string. But now since A is a string, we can add any member of our alphabet to A. So since in particular A is a member of our alphabet, then the string AA is in fact a string. And finally, since AA is a string now, and B is a member of our alphabet, by a recursive step we are allowed to add B to the right side of the string, so AAB is in fact also an element of our strings. Okay, so now that we have a recursive definition of a set of strings, we can define a property on that set recursively. And so we're actually going to have to apply our recursive definition of a string in order to give a recursive definition of the length of the string. So recall that initially we added the empty string to our set of strings, and so we need to begin by first defining what the length of the empty string is. And since the empty string is defined to have no members of the alphabet in it, we're going to define the length of the empty string to be 0. So now recall, in the recursive definition of a string, we specified how to create new strings by simply adding a member of the alphabet to the right of an already defined string. So we are going to define the length of a string defined at the recursive step of a string. So recall that at the recursive step of the definition of the string, we took a previously defined member of our set of strings and added a member of the alphabet to the right. So now we want to define the length of a string of this form, and so we're simply going to define it to be the length of W as previously defined plus 1. So as we add a member of our alphabet to the right of a previously defined string, we're simply going to add 1 to the length. And so this gives a recursive definition for the length of a string following the recursive definition of a string. So let's go through a particular example. So let's consider our bit strings. So the length of the empty string is going to be 0, and then notice how do we form new strings. We either add 0 or 1 members of our alphabet to the right of the empty string. So our next elements of our string are 0 and 1, which are lambda and 0. So looking at the length of lambda 0, that is the length of lambda plus 1. So the length of 0 is simply 0 plus 1, which is 1. Similarly, the length of 1, which is lambda 1, is the length of lambda, which is 0 plus 1. So the lengths of strings with 1 bit in them have length 1, which makes sense. As we add new members of our alphabet onto the right, we continue to add to the length by 1. So essentially, the length of a string is just going to be the number of bits that occur within it.